All right, what's up, y'all? Ryan Schubel with Straight Data Science here. So, in the topic today, I want to talk about linear discriminant analysis, and this is a way to reduce high dimensional data sets into smaller, more manageable data sets. So, there's a few different ways to do this. I actually have three videos out: SVM, PCA, and LDA. This is linear discriminant analysis. So, they're all kind of like coupled together. They're all kind of similar, but they're kind of different too. Okay. So, this particular version is a supervised method to take a big data set or data set with a lot of columns and reduce it to fewer and fewer columns so we can understand what really has the most statistical influence on the target variable. That's what we're trying to predict. Okay, so we're taking combinations of features that best separate two or more classes, right? And unlike PCA, which is unsupervised, this is a supervised method. So unsupervised is kind of like clustering, like you dump all the data into the computer in an unsupervised method, and the computer will tell you what's going on. In a supervised methodology, you tell the computer, this is what I would expect, and how can you help me to train and test the model and get close enough to making accurate predictions, right? So supervised, you know what the outcome is. Unsupervised, you really don't know what the outcome is. You're telling the computer, you tell me what I need to do, okay? So it's common to use classification problems, but again, this is a supervised learning method, so it's a little bit different from unsupervised, right? So let me go ahead and create a hypothetical data set because I don't have the actual data, but this is very realistic. I want to look at credit scores, debt to income, loan amount, interest rate, employment, length, delinquency rate, revolving balance, and the annual income. And based on this, I'm going to create a small feature engineered column called default probability. So I'm taking each of these features from credit score up to annual income, adding in a small mathematical impact or a representation, right, to create my own feature based on all these other features, right? That's what feature engineering is. And then based on that, I'm going to take the exponential logarithm of that and predict whether or not these loans will default. So if I had the default history, I could just use it. Okay, these loans worked out, these other loans over here didn't work out too well. I don't have that, so I have to manufacture it myself. So that's what I did here. Okay, and then we take all of the independent variables, set that to the x, and put this as the dependent. So all these other variables from credit score over to annual income is the independent data set, and the dependent is the y variable or the target variable. That's what I'm trying to predict in this LDA exercise. So I hit Control Enter to refresh the cell, and I have my LDA component, right? Linear discriminant analysis component. So let me visualize this and see what this looks like in a histogram. So I love these plotly charts. You can zoom in and it's very interactive. You can actually go into this thing and then click twice and you get out and you can see a couple of defaults over here. So that's kind of helpful, right? But what's really going on here? What's really happening here? With the PCA analysis, I have videos on these three. I did this earlier today. So I have the PCA. This is more like maximizing the variance of different features in a data set, and this is unsupervised. The LDA is supervised, right? We maximize class separability, and the SVM, support vector machine, is classifying observations, right? So classification is basically like assigning a label. Is this going to be a default or a non-default? So PCA will give us a 2D scatter plot by default. SVM shows us margins and support vectors, and there's really no way to plot an SVM, but you can map an SVM to a PCA, you can plot that. And LDA is just a one-dimensional projection, and it's a classifier or classification tool, okay? So let me go ahead and run this next module down here. So I'm using log regression, and I can see the model is performing pretty well. I get high, that's perfect, 1.0, 0.99 is great, that's what I'm looking for. This is a little bit low, and that is too, and that's okay. This video is not about undersampling and oversampling, but when you have these data sets where one part of the population is underrepresented, like just think about it, there's not going to be too many defaults, but there will be some. But if you don't have too many incidences of a default, how do you train a machine to predict the default, right? If you have 10, let's say 10,000 or even 100,000 loans that have been paid off successfully, and maybe 12 that haven't, the machine is not really going to be able to learn too well on 12 examples because it knows what 100,000 is. But 12 is so small, like it doesn't really have the opportunity to learn. So there's ways to handle that. I'm not going to get into that in this video. That's not what this is about, but I do have other videos that speak explicitly to that topic. So let me go down here and refresh this. So we have the model, it's trained, it's performing pretty well. Again, coming up a little bit short over here. That's okay. I'm not going to worry about that too much. This is an LDA video. It's not a smoked video. So now I have my examples. Now I can see which of these features have an impact on the target variable, right? So if I go back over here, remember, we picked the independent features right here. This is the independent, it's basically credit score over to annual income. So everything except for default and default probability, I want to calculate the default probability and show the model what a default looks like based on the default probability, right? So that is the target. That's what I'm trying to predict. And these are the independent features. So now how can I tell which features have the most impact on the target variable, which is probability of default? So when I do this feature importance exercise, I can see that the loan amount, let's see, it has the most influence, 1.6 times the influence over here. LDA coefficient, interest rate has a lot of influence, and debt to income ratio has a lot of influence. So if I was a loan officer or a mortgage officer or whatever the title is, I'm not even sure. So I would look at the loan amount, the interest rate, and the debt to income ratio, because most of the time that is going to determine whether or not a person or a small business will default on the loan, right? Like you have annual income, the lower the annual income, the more likely it's going to have an impact, right? But this is actually like a negative impact or negative importance, and a negative credit score. Think about this. If you have like a really low credit score, do you really want to give a loan to this person or to this small business? Probably not. If you have really low annual income, do you really want to give a loan to this small business? Probably not, right? But if the debt to income ratio is in alignment and the interest rate is relatively low and the loan amount is relatively low, then yeah, then I'll probably do business with this person, right? And we look at delinquency rate, that does have an impact on the target variable. And revolving balance has an impact, and even employment length. But of all these things, employment length really matters the least, and the loan amount matters the most. Okay, if you think about that, I think that pretty much made sense. We did the analysis. I didn't know that before I ran the analysis, but I think that makes sense after the model told me that. So if the loan amount is huge, if you borrow $100 million, is that person going to default? There's probably a good chance they're going to default, right? Because you're basically giving them a huge sum of money. And what is the motivation for that person to repay the loan? It's not that much, right? If you give a smaller loan, 10,000, probably going to be repaid, right? 10,000 for a car, maybe, or whatever the scenario is. That's probably going to be repaid. 100 million. I don't know. I mean, you're going out on the limb there. But employment length, I didn't know that before the analysis, but it really doesn't have a big impact on the ability or the willingness of the person to repay the loan. If you've been with your employer for 20 years, 20 plus years, that's great. 2 months, that's great. Doesn't really matter in this case, okay? So I have a couple notes down here. Let me put some comments in. Each bar shows an original feature. Length of the bar shows how strong that feature contributes to the LDA, linear discriminant analysis, okay? The sign of the bar tells you the direction. Positive coefficients push a barrier towards class 1, and negative coefficients push a borrower towards class 0, okay? So class 1 is a default. So again, bigger loan amount, bigger interest rate, bigger debt to income, that's probably going to default. And if you have a negative coefficient like annual income and credit score, that is going to be more of a non-default indicator, okay? And the color goes from blue to red, just indicating the intensity of the coefficient or the maximization of the coefficient, okay? So higher loan amounts increase the likelihood of default. Higher interest rates are associated with more default risk. That's pretty much common sense. Classic risk factor indicates default likelihood. Debt to income ratio. Higher income reduces the likelihood of default. Okay, it's pretty much common sense at this point. Higher credit scores reduce the probability of default. So what did we do here? We did a LDA, linear discriminant analysis. The mathematical basis for this is to use eigenvalues to decompose, to maximize the ratio between the class variances within class variances, okay? And we find the axes that best support these classes. So again, we're working with high dimensional data. In this case, it wasn't too many columns. It was like 8 or 9 columns, whatever it was. But and in a lot of cases, you're dealing with dozens of columns or sometimes even hundreds. You don't want the machine learning model to have to learn hundreds of columns of data, and maybe it could mislearn something. I don't think it will make a mistake, but if you're feeding in a bunch of irrelevant data, it's just going to increase the computational time, and the model could mislearn or could learn the wrong thing, right? So you want to see what really has an impact statistically on the target variable and use those features and only those features. You don't want to just throw in the entire thing. You want to see what's going to have an impact and focus on that, okay? So this basically reduces high dimensional data into low dimensional data space, and the number of dimensions is limited, again, to reduce computational processing power, and so the model doesn't mislearn or learn the wrong thing, okay? So PCA is principal component analysis. This can be used as a pre-processing step to reduce noise. LDA is applied to reduce dimensions and focus on class separability, and SVM often benefits from well processed and redundant data. I am going to cut and paste this out. I'm going to put this last because the focus was on this one this time. Okay. And again, I'll share all this code with you guys when I post the video later today. In conclusion, this can be used for visualization and emphasizes on separating classes from high dimensional data into low dimensional data and projects data into a space that makes it easier to distinguish between different groups or different subsets of data, right? So we're taking something that's somewhat complex and reducing it to something that's basically simplified, okay? So that is it. Thanks for your time and attention today. I appreciate that. And I'm going to wrap it up here, and I will see you guys in the next video, which is coming out soon. Thanks. Bye.